তো আজকে আমরা কিছু কোড কনভার্সন নিয়ে আলোচনা করব। ডিজিটাল ইলেকট্রনিক্সে আমরা বিভিন্ন কোড ইউজ করি বিভিন্ন সময়। তার মধ্যে একটা কোড হচ্ছে XS3 কোড। তো ফার্স্টে আমরা XS3 কোড নিয়ে আলোচনা করব যে XS3 কোডটা কি এবং কিভাবে আমরা সেটাকে ক্যালকুলেট করতে পারি, সেসব জিনিসগুলো। ওকে, তো ফার্স্টে আমরা XS3 কোড নিয়ে আলোচনা করব, তারপর আমরা এরকম আরেকটা কোড নিয়ে আলোচনা করব এবং তাদের কনভার্সন মেকানিজম বা সার্কিট সেগুলো দেখব। তো ফার্স্টে স্টার্ট উইথ XS3 কোড। It is known as like that XS3 code. XS3 code basically it's very simple. Suppose you have given a decimal number like this. Now you have to convert it to its XS3 code. So first of all, what you have to do, you have to add 3 with individual digits. So this will become 4 and this will become 5. Now you have to convert these 4 and 5 to binary. So 4 means 0 1 0 0, 5 means 0 1 0 1. So your XS3 code of 12, it will be this in binary. So this is basically XS3 code, as simple as that. একদম সিম্পল।
XS3 বলে ওই 3 দিয়ে অ্যাড করতে হলো, তাই তো?
একদম XS3 বলে 3 দিয়ে অ্যাড করতে হবে। ওকে, সিমিলারলি যে কোনো নাম্বার, you given any number, suppose 29 is given to you. So individually with 2 you will add 3, with 9 again you will add 3. It becomes 5 and 12. Now convert 5 to binary. So that is again 0 1 0 1. Convert 12 to binary. That is 1 1 0 0. Now you will write it like that: 0 1 0 1 1 1 0 0. So that will become 29's equivalent XS3 code. Now here the key feature, which is most important, but what you have to keep in your mind, the key feature of the XS3 code is self-complementing. XS3 codes are self-complementing. It is self-complementing. XS3 codes are self-complementing. That means one's complement of an XS3 number. Again, I'm repeating why it is self-complementing. I'm justifying just that. That is, one's complement of an XS3 number is the XS3 code for the 9th complement of the corresponding decimal number. Again, I'm saying one's complement of an XS3 number. Suppose this is an XS3 number. One's complement of this number. Okay, is the XS3 code for the 9th complement of the corresponding decimal number. কিরকম? Let's see that কিরকম. Suppose decimal 4. Okay, decimal 4 is given to you. Okay. So excess 3 of 4 will be how much? Excess 3 of 4 will be 4 plus 3.
Sir, your voice is breaking.
That is due to network problem. Everybody is getting my voice break.
No, sir, it's all right.
I think it is at your part. Okay, network issue. It will be okay. Otherwise, you can just log out and then again log in.
Okay, sir.
Yeah. So 4 plus 3, that is 7. So this 7 in binary, we know. This is 7 in binary. Okay. What is the ones complement of this XST code?
1000.
Yes, it is 1000. This is the ones complement of this. Now this 100 is how much? Actually, it is in decimal how much? 8. Okay. So this 8, it is basically, we can say that XS3 code of 5. 8 can be XS3 code of 5. Now, I have said that it is the 9's complement. So 5 is 9's complement of 4. How? Because if I subtract 5, I mean from 9, so I will get 4 again. So I have started from 4. I have got its XS3 code. I have recomplemented it. Whatever I have got, that is basically XS3 code of 5, which is again the 9's complement of, I mean, if I perform 9's complement of 5, then again I'm getting 4 return. So that is how it is self-complementing. I have started from 4. I have done its XS3. So that was this. I have complemented it. Whatever I have got, that is basically XS3 of 5, because 8 is XS3 of 5, you can say. So now 5 is what? 9's complement of 5 is what? Again 4. So I'm getting 4 again. I've started from 4, getting 4 again. So in that way, it is self-complementing. So this is a very vital property of XS3 codes, that XS3 codes are self-complementing. Okay. So this is about XS3 code. Nothing more than that of it. This is about XS3 code. You have to remember it like that. That XS3 code, you have to add 3 with every digit that will be given to you. And it is self-complementing in this way. That means if you perform the ones complement of the XS3, whatever you will get, that will be again the 9's complement of that number. So 5 is the 9's complement of 4. So that is the thing. Okay. Next, there is another type of code that I will discuss today. So I'm grabbing this. Another type of code is Graycode. Graycode. Now, here for the Graycode, the property is that each Graycode number differs from the previous number by a single digit. Each Graycode number differs from the previous number by a single digit. Now this gray code we have already got in our Carnot maps, because in the Carnot map we have seen that when we write it 0 0 0 1, then we got to 1 1 and then 1 0. That is to maintain this property that every digit will differ by a single digit. Over here this 0 is become 1, over here this 0 is becoming 1, over here this 1 is becoming 0. So at every stage only single digit is changing. So that is why in Carnot map also we follow this. Otherwise if I write 0 0 then 0 1 then 1 0 then 1 1, here if you check it, two digits are getting changed, digits are getting changed. So to keep that parity we use this sequence in Carnot map, not this. We use this sequence in Carnot map. So as I told you that each gray code it will differ from the previous number by a single digit. Now suppose from decimal 7 to 8, suppose from decimal 7 to 8 the gray code numbers change like this. Suppose decimal 7 to 8, the gray code number will change like that. This is 0 1 0 0, and this is 1 1 0 0. So here single digit is getting changed only. That is the most significant bit here. Now the thing is that how to get this gray code. So basically a 3-bit gray code may be obtained by reflecting the 2-bit code about an axis, and at the end of the code you have to assign a 3rd bit as 0 above the axis and 1 below the axis. I'm showing you how we are getting it. So suppose we have got 2-bit gray codes. So we know what is 2-bit gray codes. Whatever we use in Carnot map, that is 2-bit gray code. So this is your 2-bit gray code 0 0. This is your 2-bit gray codes. Now if I take it as an axis, now here I'm writing again. Now I'm converting 2-bit gray code to 3-bit gray code. Check it. So 0 0 I'm writing, 0 1 1 1 1 0 I'm writing. Okay. Now here I have to reflect it. Below the axis I will reflect the same thing. That is, over here I will write 1 0, then 1 1, then 0 1, then 0 0. Now above the axis I will put 0. Above the axis as a 3rd bit I will put 0, and below the axis as a 3rd bit I will put 1. So this will become 2-bit to 3-bit gray code. And from this property of the gray code we can say that these gray codes are self-reflecting codes. These are self-reflecting codes. You check, it is self-reflecting. From here to here we are reflecting it. So it's a self-reflecting codes. So this is about the gray code. Similarly, from 3-bit to 4-bit you can do in the same way. All these will come. After that there will be an axis. Okay, it will be reflected. And then again for first 8, you will put 0. Rest of the 8 below the axis, you will put 1. So that will become 3 to 4 bit. So in this way, you can move on in case of gray codes. Okay. Now, come to the conversion mechanism. Suppose we want to get binary to gray. Suppose we want to convert binary to gray. How to do that? How to get that? Before starting this conversion, I want to mention here that this gray code has some problem. Gray code has some problem. What problem? Basically, these gray codes, it belongs to the class of minimum changes code. It belongs to the class of minimum change code. And you know, each gray code number differs from the previous number by a single digit only. That's its property, that each gray code number differs from the previous number by a single digit only. Okay, that is a problem. That is a problem in case of you can say when devices are synchronized with each other. Actually, how much digits will be changed from one state to another state, that will be easier. That will be much easier for any device to differentiate between two states. Actually, what we do in binary, we try to differentiate between two states always. Okay, 2 or 3 or different states, right? Now those states, if we can do that by changing several bits, that will be easier for any device to capture that changes. So here in gray code, only single digit is changing from one state to another state. And that is a bit disadvantage for these codes. যদি এখানে এক এক জায়গায় দুটো বিট চেঞ্জ হতো বা তিনটেই যদি চেঞ্জ হতো, তাহলে সেটা যে কোনো ডিভাইসের পক্ষে বুঝতে আরো সুবিধা হতো। আর যেহেতু এখানে একটাই বিট চেঞ্জ হচ্ছে, যে কোনো ডিভাইসের পক্ষে সেটাকে ক্যাপচার করতে একটু ডিসঅ্যাডভান্টেজ হতে পারে। প্রশ্ন হচ্ছে যে তাও কেন তোমরা এটা ইউজ করবো, আমরা এটা ইউজ করবো, তার কারণ একটা বিট চেঞ্জ মানে আমার সিস্টেমের এই যে চেঞ্জ, একটা স্টেট থেকে একটা স্টেট যে চেঞ্জ হচ্ছে, তার টাইমটা অনেক কম লাগছে। So that is again an advantage. So that is why we use, at some places we use these gray codes. Now another disadvantage that these gray codes have is that it is an unweighted code. Gray code, it is an unweighted code. Unweighted code means we are not assigning any weight, any value with these bits. Actually, in some mechanism, you can assign some extra weight to the bits to make it more composed, you can say. Again, ultimately to make it more understandable by the devices. So this is again an unweighted code. That is also a bit disadvantage. So that is why these gray codes, these are not suitable for any arithmetic operations. You have to remember that these gray codes are not suitable for any arithmetic operations. Kono arithmetic operations er jonno we will not go for gray code, right? Now come to the conversion, binary to gray code. First conversion we will see binary to gray code. Next conversion we will see gray code to binary. Okay, so binary to gray code. Binary to gray code rules are like that. MSB will be same. That is most significant bit will be same. I'm writing the rule for you here. MSB will be same. So there will be nothing change in the MSB of the given binary number. Then going left to right, add each pair of binary digits to get next gray code. So going left to right, add each pair of binary digits to get the next gray code. And that's all. So suppose we have given a binary number. Suppose we have given a binary. আচ্ছা তোদের স্ক্রিনটা বড় আসছে তো এখানে ফুল স্ক্রিন আসছে তো?
হ্যাঁ স্যার।
Yes, sir.
Okay. So suppose we have given a binary number like this: 1 0 1 1 0. This is the binary number. Okay, this is the binary number. Now we have to convert it to gray code. So MSB will be same. So which is MSB? This is MSB, most significant bit. MSB means most significant bit, and this is LSB, least significant bit. So MSB will be same. So 1 is coming here. Now I have said going left to right, add each binary digits, add each pair of binary digits to get next gray code. So 1 plus 0. So 1 plus 0 is what? 1. 0 plus 1 is what? 1. 1 plus 1 is what? 0. And 1 and 0 is what? Again 1. So this is the equivalent gray code number. Remember over here, when I have made 1 1 0, I have not considered the carry, because you know in 1 1 it becomes 0 carry, there is carry 1. I have not considered that carry. I have simply going left to right added the pair of binary consecutive pair of binary numbers to get the gray code. So 1 0, first of all this MSB will come as it is, then each pair of binary digit is added and we are putting it in the as the next gray code number. So that is the equivalent gray code number. Now the reverse one. The reverse one is gray code to binary. So reverse one is gray code to binary. Gray code to binary. So here again the rule is MSB will be same. First rule ta same, MSB will be same. Second হচ্ছে add each binary digit. Second rule টা একটু চেঞ্জ আছে, সেটা হচ্ছে add each binary digit generated to the gray code digit in the next adjacent position. Add each binary digit generated to the gray code digit in the next adjacent position. Again, I'm saying add each binary digit generated, যে binary digit টা generate করছে gray code থেকে, because now we are going to convert gray code to binary. So add each binary digit generated that will be added with the gray code digit in the next adjacent position. How it is? This is my gray code again. This I have converted from binary to gray. So this is my gray code. So now, first of all, again, 1 will come, MSB will come as it is. Okay, so 1 is coming as it is. Now, this time I will add this one and this one. Previously, I was adding this one. Now I'm adding this one because this binary digit has been generated. So I'm adding this one and this one. This and this one. For you, I'm making it an arrow. This one and this one. So 1 1, it will become 0. Next, this one and this one. Okay, so 0 1, that will become 1. Then this one and this 0, so 1 and 0, it will become 1. And finally this one and this one, so 1 1, that will become 0. And you see, to check it, we have started from here, we have got it back. So this was binary, this was gray, this was again binary. So that is how we can convert from gray to binary or binary to gray. Okay, that is how we can convert from gray to binary or binary to gray. Right. Is it okay?
Okay, sir.
Okay, fine. So now we will see another conversion. We will see another very simple conversion, and that is binary to BCD conversion. Before, later on I will draw this circuit. Okay, আমরা সার্কিটটাকে ড্র করি। এর সার্কিটটা আমরা কি করে ড্র করব? এই বাইনারি টু গ্রে এবং গ্রে টু বাইনারি বা XS3 কোড, বাইনারি টু XS3 and all that, বা XS3 to this. So first of all, binary to gray code. Okay, binary code to gray code conversion. তো বাইনারি কোড টু গ্রে কোড কনভার্সন তুমি দুরকম ভাবে করতে পারো। বাইনারি টু গ্রে এবং গ্রে টু বাইনারি দুরকম ভাবে করতে পারো। এক হচ্ছে তুমি সিম্পলি এর ট্রুথ টেবিল একে কার্নফ ম্যাপ দিয়ে করতে পারো। ট্রুথ টেবিল একে কার্নফ ম্যাপ দিয়ে করতে পারো। দ্যাট উইল টেক সাম টাইম, বাট ইউ ক্যান ডু দ্যাট। যে তুমি চারটে ভ্যারিয়েবল নিলে বাইনারি কোডে ABCD এবং তার করেসপন্ডিং গ্রে কোড গুলো নিলে, এবার পরপর চারটে বাইনারি কোড তুমি পরপর 0000 থেকে 1111 অবধি বসিয়ে নিলে, তার সঙ্গে করেসপন্ডিং যে গ্রে কোড গুলো সেগুলো তুমি লিখতে থাকছো চারটে রিফ্লেকশনে, এবং করার পর সেখানে তুমি দুরকম ভাবে করতে পারো। সেটা হচ্ছে, এক হলো তুমি ট্রুথ টেবিল আঁকলে পরপর, মানে ABCD বাইনারি কোড নিলে, তার করেসপন্ডিং গ্রে কোড নিলে, ধরো G0 G1 G2 G3 সামথিং লাইক দ্যাট। এবার বাইনারি কোড 0000, গ্রে কোড তখন 0000। বাইনারি কোড যখন 1000, গ্রে কোড তখন এগেন 1000। তারপরে বাইনারি কোড যখন 0100, গ্রে কোড তখন হয়ে যাবে 1100। তো এরকম ভাবে তুমি কার্নফ ম্যাপে ট্রুথ টেবিল এঁকে তাকে এবার চারটে কার্নফ ম্যাপ করলে, একটা G0 এর জন্য, একটা G1 এর জন্য, একটা G2 এর জন্য, একটা G3 এর জন্য করলে, করার পর যে তুমি G0 G1 G2 G3 যে ইকুয়েশনস গুলো পেলে, সেগুলো দিয়ে সিম্পলি তুমি সার্কিটটা ড্র করলে। এটা একটা প্রসেস, দ্যাট প্রসেস উইল টেক আ বিট টাইম। আরেকটা মেথড যেটা তুমি ইউজ করতে পারো, মানে এত কিছু না করে একটু শর্টকাট কাইন্ড অফ মেথড, সেটা হচ্ছে, তুমি তো রুলটা জেনে গেছো যে বাইনারি টু গ্রে কোড আমি করছি, তাহলে আমার MSB উইল বি সেম, এবং আমাকে প্রত্যেকটা বাইনারি ডিজিটকে অ্যাড করে করে এগোতে হবে। এবার এখানে যদি তুমি দেখো, যে আমরা দেখছি যে প্রত্যেকটা বাইনারি ডিজিটকে অ্যাড করছি, মানে 10 তখন 1 হচ্ছে, আর 11 তখন 0 হচ্ছে। ঠিক আছে, 10 যখন তখন 1 তাই হবে, 11 যখন তখন 0। তাহলে এই প্রপার্টিটা যদি আমাকে পেতে হয়, 1 মানে সিমিলার টাইপ অফ, বা 00 যখন তখন 0 হবে, 01 হলে 1 হবে। তার মানে সিমিলার টাইপ অফ বিট থাকলে আমার 0 হবে, ডিসিমিলার টাইপ অফ বিট থাকলে আমার 1 হবে। তো এই প্রপার্টিটা অ্যাচিভ করার জন্য আমি কোন গেট ইউজ করতে পারি? who can tell me যে এই প্রপার্টিটা, যে সিমিলার টাইপ অফ বিট উইল গিভ মি 0, dissimilar type of bits will give me 1. So what logic gate we can use for this property? Who can tell us? আমরা অলরেডি করেছি। সিমিলার টাইপ অফ বিট থাকলে আমার 0 হবে, ডিসিমিলার টাইপ অফ বিট থাকলে 1 হবে। এই প্রপার্টিটা কোন লজিক গেট আমাকে দেয়? কাম অন, ইউ ক্যান সে।
Or
Yes, it is. Repeat, please.
XOR.
XOR. XOR gate will provide us this property. That similar type of bits whenever there will be similar type of bits, it will produce 0. Dissimilar bits will produce 1. So XOR property will give us, XOR will give us that thing. So simply, instead of going into the details of truth tables and Carnot maps and all that, we can draw the logic diagram very easily from this assumption. And what is that? So that will be, suppose here are your binary digits A, B, C, D. Okay, and suppose here you are writing your output Graycode digits C0, G1, G2, G3. My rule was MSB will be same, so this is my MSB for binary, so it will come as it is. MSB is same, so it will come as it is. Now I was adding each binary digits to negate the next Graycode digit. Okay, I was adding each binary digit to get next Graycode digit. So here I will use 3 XOR gates. Okay, and what we will do? 3 XOR gates. What we will do? We will simply take this as one input and take this as another input, and that will come here. Similarly, I will take this as one input. I will take this as one input. It will come here. I will take this as one input. I will take this as one input, and it will come here. You check it. Just check it. This is my binary code. This is my Graycode. Okay. Got it? Got it? Any confusion here? Please tell me. Any confusion? You can check it. This is binary. This is binary. And this is its corresponding gray code. So you can check it. Any number, take any number, you just check it. It will give you gray code. And similarly, if it is okay, is it okay? Is it fine? Are you getting me?
It's okay, sir.
It's okay now. So if it is okay, then similarly, you can do the reverse one, gray code to binary code. Just try to make gray code to binary code. It was given, the rule was MSB will be same again, and from gray to binary, what we are doing, we was adding this with this one. Okay, so just try to do that. Gray to binary again. Gray to binary, if you remember, I said that in case of gray to binary, MSB will be same, and we will add each binary digit that is generated to the gray code digit in the next adjacent position. So please try to draw the reverse one, gray to binary. Gray to binary draw করার চেষ্টা করো তো।